Okay, part 3. These questions come from chapter 5, of the chapter dealing with exponential and logarithmic functions. Question 11, parts A and B are the graphs of exponential functions. This one happens to be exponential growth because it's a base larger than 1. This is exponential decay because the base is between 0 and 1. So the steps we learned for graphing an exponential function are to first find a horizontal asymptote, which is determined by the value after the exponential term here, moving the graph up or down. Plus 2 moves the graph up 2 units, which also moves the horizontal asymptote up 2 units. And the next step is to find the Y-intercept by letting x equal 0. If x is 0, 0 minus 1 is negative 1. 2 to the negative 1 is 1/2. 1/2 plus 2 is 2.5, which is about right there. Now to complete the graph, we need some more points. Now this is an exponential growth function, which means the graph from left to right is very, very close to the horizontal asymptote, but it continues to increase rapidly as x gets larger and larger. So we want to find the x values over here to give us a good idea of the rate of increase, or how the graph is increasing. So choose x values beyond 0, x equals 1, x equals 2, or x equals 3. If x equals 1, we get 2 to the 0 plus 2, which is 3. So 1 comma 3. If x equals 2, 2 minus 1 is 1. 2 to the 1 plus 2 is equal to 4. So 2 comma 4. If x equals 3, 3 minus 1 is 2. 2 squared is 4. 4 plus 2 is 6. This is a graph of that shape. Very similar on part B, we start with this number to find our horizontal asymptote. It's negative 1. Okay, now we use x equals 0 to find our y-intercept. If x is 0, 1/3 of the 0 is 1. 1 minus 1 is 0. Now since this is a decay function, the graph from left to right is decreasing. Okay, the y values are getting smaller. So I want to choose x values on the left side of the y-axis so we can get a good idea of how the graph is decreasing before it eventually begins to level out. So for our x table, I'm going to choose values on the left side of the y-axis. If x is negative 1, 1/3 to the negative 1 is 3. 3 minus 1 is 2. Okay. And 1/3 to the negative 2 is the same as 3 squared, which is 9. 9 minus 1 is 8. So negative 2 comma 8. This is a graph like that. Okay, 12. A, B, and C we need to evaluate. Evaluate means give the value of the expression. Log base 3 of 81 has a value. Now, one of the properties of logarithms that we learned about is a logarithm with a base of 3 would cancel an expression that has a base of 3. So if we can change 81 into 3 to the 4th power, then the log base 3 cancels the base of 3, leaving a 4. So the answer is 4. Same on part B. We need to try to write 5 as 25 to some power. It turns out that 5 is the same as 25 to the 1/2, because any 1/2 power is the same as the square root, and the square root of 25 is 5. So the log base 5, or the log base 25 of 25 to the 1/2. 25, the two bases of 25 cancel, leaving a 1/2. Now the natural log is a logarithm with a base of e, even though it's never written. So a natural log cancels with the base of e, leaving a 3. Okay, expand or condense each logarithmic expression. In this case we're expanding. This is an example of the product rule. Product rule states that if you're taking the logarithm of a product, that can be expanded into multiple logarithms separated by addition. So there's going to be the log base 4 of x squared plus log base 4 of y plus log base 4 of z to the third. Now there was another property we learned called the power property. If you're taking the logarithm of an expression that has an exponent, then the exponent can come down to the front of each logarithm. So it's going to be 2 log base 4 of x plus log base 4 of y plus 3 times log base 4 of z. Now when we have multiple logarithms, we're going to condense that into a single logarithm using the power property, the quotient property, and the product property. So if you notice, the last property we applied here was the power property. We brought exponents down to the front of the logarithm. And that's what you do when you're expanding. When you're condensing, that's the one you start with. You start by moving numbers in front of logarithms back up as exponents. So all of these numbers in front of the logarithm need to move back up as exponents in the expression. So this is going to be the log of x squared minus the log of y to the fourth plus log z squared. Now condense from left to right. So starting with these two logarithmic expressions, since there's a minus sign between them, that's an example of the quotient property. These two need to be combined, forming a quotient. So log, quotient means fraction, so it's x squared over y to the fourth plus log of z squared. Now these two logarithmic expressions are separated by a plus sign. That's an example of the product property. So we need to form a product now when we condense these two logarithms. Product means multiply. So this is the log. When x squared over y to the fourth is multiplied by z squared, that results in x squared and z squared in the numerator, y to the fourth in the denominator. Solving logarithmic equations. You solve a logarithmic equation by isolating the logarithmic expression and then exponentiating both sides, or rewriting the expression in exponential form. Now this is the exponential term, or excuse me, the logarithmic term, natural log of x plus 3. We need to get this all by itself. So that means we have to add 2 to both sides. So we're going to have the natural log of x plus 3 is equal to 5. Now the natural log, again, has a base of e. If we rewrite this in exponential form, this is our base e. The 5 acts as the exponent, and the x plus 3 is no longer inside of a logarithmic function because we've rewritten this in exponential form. Now, last step to isolate x is to subtract 3 on both sides, so x is equal to e to the fifth minus 3. Now when you have a logarithmic equation with multiple logarithms, you need to condense the logarithms into a single logarithmic expression. So these two logarithms here are separated by a plus sign. This is another example of the product property. So when you condense these two logarithms, the two expressions, x minus 2 and x, need to form a product. That product would be x squared minus 2x if you multiply those together. Now we have a single logarithm. This can be rewritten in exponential form. Now 2 is the base, 3 is the exponent, and the x squared minus 2x is no longer inside of the logarithmic function because we've rewritten this in exponential form. Now if we set this equal to 0, by subtracting 2 to the third is just 8. So subtract 8 on the other side, factor and the two zeros, or the two solutions, are x equals 4 and x equals negative 2. Now, a critical mistake here is to remember the domain of a logarithm. The domain of a logarithm are numbers greater than 0. You can't, when you plug a number into a logarithmic function, that can't result in a negative number. So for example, if I took the negative 2 and plugged it in for this x, you can't take the logarithm of a negative number. That's impossible because it's not in the domain. So negative 2 is actually an extraneous solution. X equals 4 is the only solution to this. Alright, a couple of story problems here. Alright, after 20 days, the sample has been reduced to a mass. Okay, so the half-life of palladium is 4 days. They haven't given us an initial mass of the sample, but they told us after 20 days, the sample that was originally there has been reduced to a mass of 0.375. So the first question they're asking us here is, what is the initial mass of the sample? And find a function that models the mass remaining after t days have passed. So this function that we're going to be finding in part B would allow us to anticipate the mass remaining after any number of days. So let's see, what was the initial mass of the sample? We're going to have to use the fact that the half-life is 4 days, and also the fact that 20 days have passed. And what you need to think about is, after 20 days, how many half-lives have passed. If each half-life is 4 days and 20 days have passed, then that's 5 half-lives. Okay, so if we maybe think backwards, if after 20 days 0.375 is remaining, what was remaining for the half-life before that one, and then the half-life before that one, and the half-life before that one, all the way back up until we've reversed 5 half-lives, and we can figure out the original amount that way. So if we want to think about it this way, if this represents the original amount, then after 1 half-life, it reduces to some unknown amount, and then after another half-life, and then another half-life, and another half-life, and then another half-life. So here's 5 half-lives. 1, 2, 3, 4, 5. After the 5th half-life, there was 0.375. So if we go backwards and double, that should give us the original amount. So that would be 0.75, that would be 1.5, that would be 3, that would be 6, which means the original amount was 12. Because if you start with 12 and then allow 5 half-lives to occur, you would end up with 0.375 grams. Originally we had 12 grams. Now, what we learned back in chapter 5, the way that we that we model an exponential growth or an exponential decay function is it's essentially the same thing as PERT. Most students have an easy time remembering PERT. It's very, very similar to that. It's the amount at time t is equal to the original amount, a sub 0, times e to the kt. Now, we know the original amount now. What we need to find is the value of k, that stands for the growth constant, and we'll be able to write our function. So right now we have that a of t, the amount at time t, is equal to 12 times e to the kt. Now we know that after 1 half-life has passed, when t is equal to, well, after 4 days, after 1 half-life, that's 4 days. So if we allow t to equal 4, that's one of the half-lives, then 12 can now be reduced to 6. And if we divide by 12, we're going to get 1 half is equal to e to the k times 4. I'm going to take the natural log of both sides. Natural log of 1 half is equal to k times 4. Divide by 4 on both sides, we're going to get the value of k that we're looking for. The value of k is equal to the natural log of 1 half divided by 4. Now we can go back and finish our model. The amount at time t is equal to the original amount, 12 times e to the natural log of 1 half 4 times t. This is a function that models the amount at a certain time, t. Okay. Solving systems of linear equations. There's three equations, three unknowns, three variables. I'm going to look at these top two equations here. If I multiply the top equation by times by negative 2, if I times the top equation by negative 2, the top equation is going to result in negative 2x minus 4y plus 4z is equal to negative 2. The middle equation didn't do anything to the middle equation. That's going to stay 2x plus 2y minus z is equal to 6. When we now eliminate the x variable, that results in negative 2y plus 3z is equal to 4. Now, if we take the top equation now and the bottom equation, if I take the top equation and multiply that by negative 3, I'm trying to cancel the x again. The top equation is going to be negative 3x minus 6y plus 6z is equal to negative 3. This bottom equation is 3x plus 4y minus 3z is equal to 5. Eliminating the x variable results in negative 2y plus 3z is equal to 2. Now I take the equations that resulted from that elimination. That's going to, if I, let's multiply this one here by negative 1. So if I multiply this times by negative 1, that's going to be 2y minus 3z is equal to negative 2. This equation here is negative 2y plus 3z equal to 4. This results in 0 equal 2. 0 does not equal 2, therefore there's no solution. Now part B is going to be very similar, except when you get to this step, you're going to, both variables are not going to cancel out. So myself a little more room here. If I take the top two equations and add them, so I'm going to have x minus 2y plus 3z equal to 1, and x plus 2y. If I add the top two equations without multiplying either of them, the y's will cancel, leaving 2x plus 2z is equal to 14. Now if I take the bottom two equations here and multiply the bottom one here by negative 1, so that becomes negative 3x minus 2y plus 5z equal to negative 3. Middle equation there is going to stay the same. X plus 2y minus z equal to 13. Eliminate y, leaves negative 2x plus 4z is equal to 10. Now take the two equations that result and perform elimination again. That results in 6z equal to 24, which means that z is equal to 4. Now going back up a step into one of these two equations, if z is equal to 4, this z, for example, if this z is equal to 4, then 2 times 4 is 8, so this is really an 8. And if you subtract 8 from 14, you get a 6. If you divide 6 by the 2, you get that x is equal to 3. And now if we take z is equal to 4 and x is equal to 3 up into one of the original equations, if x is equal to 3, then that's a 3. If z is equal to 4, then that's plus 12. 3 plus 12 is 15. If you take 15 from 1, you're going to end up with negative 14. So we're going to have negative 2y is equal to negative 14. Divide by negative 2, which gives us y equals 7. So the solution is 3, comma 7, comma 4. Okay. Find the price of the coffee, the juice, and the donuts. These are what we don't know, coffee, juice, and donuts. So if we let C equal price of coffee, we can let J equal the price of juice. We're going to let D equal the price of donuts. Now what we need are three equations that relate the variables to the price. Okay? And luckily we have three different people buying three different amounts or quantities of these three items, resulting in different amounts that they paid. So those are the three equations. We can build an equation from each purchase, how much Ann bought, Barry bought, and Kathy bought. So starting with Ann orders 2 coffees, 1 juice, and 2 donuts, and that pays $6. And she paid $6.25. Barry orders 1 coffee and 3 donuts, no juice, and he pays $3.75. Kathy orders 3 coffees, 1 juice, and 4 donuts, and pays $9.25. I think the hardest part of the story problem is getting it set up. Now that it's set up, I'm going to leave this for you to practice solving. You can check the solutions on the solutions part of the website for this review. And it seems like there's a typo here. That should be an x plus 1, not x plus exclamation mark. So partial fraction decomposition, what we need to begin first is writing the form of the partial fraction. We have a repeated linear factor here, the x plus 1 squared, and then a non-repeated linear factor of x. So the non-repeated is going to be a over x, but the repeated linear factor is going to be b over x plus 1 plus c over x plus 1 squared. We have to repeat this until we have the same exponent here as the number of times that linear factor is repeated. So this is the form of the partial fraction. Now we need to find the values of a, b, and c. So if we multiply both sides of the equation by the lowest common denominator, that's going to be multiplying this by x times x plus 1 squared. Same thing over here. This is multiplied by x times x plus 1 squared. That's going to eliminate the denominator, leaving 3x plus 2. Now, this LCD here needs to multiply to each piece separately. Now, when it multiplies to the a piece, the single x would eliminate with that single x, leaving a to multiply with x plus 1 squared. Now when the LCD multiplies to the middle term here, the determinant of b, one of these x plus 1s would cancel with one of these x plus 1s, leaving b to multiply with x times x plus 1. And what multiplies to the c term, the x plus 1 squared cancels with x plus 1 squared, leaving c times x. Now if we simplify a little bit here, x plus 1 squared, and then multiplied it with a, that's going to be ax squared plus 2ax plus a. And if we simplify a little bit here, there's going to be bx squared plus bx. And here, nothing to simplify. Now rearranging and grouping similar terms together, we have an ax squared and a bx squared. If you factor out the x squared, it's going to be a plus b, and factor out the x squared behind it. Here we have a linear term, 2ax, and then bx. and cx. So if we group those together and factor out the x, we're going to have 2a plus b plus c, factor out the x, and we have this single constant here plus a. Now we need to equate coefficients. Okay, this right here, we have an x squared term, we have an x term, we have a constant. Over here we just have a linear, an x term, and a constant, so we need to have an x squared term to compare it to the right side. The coefficient of this x squared term is 0. The coefficient of this x squared term is a plus b. So we conclude that a plus b is equal to 0. The coefficient of the linear term is 3. The coefficient of this linear term is 2a plus b plus c. So we conclude that 2a plus b plus c is equal to 3. Now the constant 2 is equal to the constant over here, which is a. So we say that a is equal to 2. Now we try to figure out the remaining values of b and c. If we know a equals 2 and a plus b is equal to 0, b has to be negative 2. And if a is 2, 2 times 2 is 4, 4 plus negative 2 is 2, 2 plus what equals 3, so that means that c has to be equal to 1. So we rewrite now, a is equal to 2, so it's 2 over x plus negative 2 over x plus 1 over x plus 1 squared. Now these appear to be very similar, but the key is this x plus 1 is non-repeated. It's just x plus 1. So the form of this is a over x plus b over this x plus 1. This one's going to be a little bit quicker to solve. If we multiply both sides now by the lowest common denominator, it's going to cancel there. So 3x plus 2 is equal to a times x plus 1 plus b times x. Now rearranging ax, and this is going to be an a, this is going to be a plus b x plus a. Equating coefficients now, 3 is a coefficient of x, and a plus b is a coefficient of x. So a plus b is equal to 3. 2 and a are constants, so they have the same value. A is equal to 2, which means b is equal to 1. We have 2 over x plus 1 over x plus 1. Multiplying two matrices only works when you compare their dimensions. Okay. This is a 3 by 2. What's the number of rows? There's 3 rows, 1, 2, 3, and 2 columns, right? 1 and 2. So it's a 3 by 2. This one here is a 2 by 2. The inside dimensions here say that the multiplication is possible only if those dimensions are the same. The number of columns in matrix 1 has to be the same as the number of rows in matrix 2. The outside numbers state that this is going to be a 3 by 2 matrix when multiplied together. So a 3 by 2 matrix has 9 entries. This entry here, we need to go across that row and down that column. The 2 times 3 makes a negative 6, and the 4 times 4 makes 16. Adding those two is going to give you a 10. And that's how the multiplication works. Whatever entry you want, like this entry here, okay, that's going across the middle row and down this column. So go across the middle row and down the column. Negative 1 times negative 1 is 1. Negative 3 times negative 2 is 6. 1 plus 6 is a 7. well, let's go on. Let's complete this first column here. If I want the next entry, that's this row and that column. -3 times -1 is 3. -3 times 4 is -12. 3 and then -12 makes -9. Now we move down here. Same column, different row. 0 times -3 is 0. 4 times -2 is -8. 0 and -8 added together is -8. And then move back to the top row, down that column. 2 times -1 is -2. 4 times -2 is -8. -2 and -8 makes -10. And then we need drop down to this row. 0 times -1 is 0. -2 times -2 is 4. 0 plus 4 is 4. Evaluate a 3 by 3 determinant. I notice that this column includes a 0 right here. So I'm going to expand along this column using the cofactors and the minors. And if we choose 2 as a cofactor and cross out the row and column containing that 2, the minor that's left over is this 2 by 2 determinant, -6, 1, 2, -3. When we subtract, if we use this now, this 3 as a cofactor and cross out the row and column, that's going to leave a minor of 0, 3, 2, -3. And then we have to add, if we use 0 as a cofactor, it actually doesn't matter what the minor is, because 0 times anything is just going to be 0, so we don't have to bother with that one. Now, the determinant of a 2 by 2 matrix is A times D, which is 18, minus B times C, which is 2. Same thing, this one here, it's A times D, which is 0, minus B times C, which is 6. 18 minus 2 is 16, times 2 is 32. -3 times -6 is 18. That results in a 50. This will be the end of part 3.